Good morning, everybody. Our talk will be divided into two parts. I'll start the first part. I'll discuss the new challenges and requirements of the machine learning workloads, and then I'll talk about the techniques we are applying. The techniques we are applying for handling those challenges, and I'll show some results from lab testing and from simulation, very interesting results. And then I'll hand off for Mehak to talk about the software part. Okay, so let's start. So what are the machine learning unique requirements? So first of all, the bandwidth that is generated by this workload is very high. It can generate 100% utilization on the network for long periods of time. The second part is that the flows are very small in number, relatively, and they are very high bandwidth and last for a long period of time. And under those conditions, still you would want to optimize tail latency and flow completion time, and you want to provide and minimize the number of checkpoints, because in a machine learning workload it can last for hours or days, so you don't want to lose any of the data, so there's a lot of checkpoint in the middle. So you want the network to be very resilient. So the main point is that the network is required to help in reducing and addressing those requirements and reduce the job completion time. So what is the result of these challenges? So the fact that there is a small number of flows and the flow is very high in bandwidth can result in load balancing issues in reducing the network utilization. The second one is that the high utilization of the network for long periods of time can create congestion in different locations in the network. And again, this congestion reduces the bandwidth of the network and the efficiency of the network. So we suggest two techniques to handle these challenges, and we apply them in our DDC architecture. So this, the two of them is a kind of obvious solutions. One of them is to do better load balancing, and the way to do it is to do cell-based spraying of all the data in all the available paths, and we'll discuss that in following slides. And the second one is, instead of pushing the data into the destination, do end-to-end scheduling and prevent the congestion in the first place. So these two techniques allows us to deal with these network challenges. So how do we handle the load balancing? So when high bandwidth flows, when using traditional architecture, then you use either ECMP or other flow-based load balancing, which are not efficient when the bandwidth is very high and the number of flows is relatively small. So the suggestion here is to take any number of flows that come from any GPU. It can be a single flow or multiple flows, and then when sending them over from the top of rack to the spine or to any layer, between any two layers, you just take the flow and split it evenly on all the paths. This way you are getting kind of optimal load balancing using all the available paths in the same way. So, of course, when you do that, you have to cope with the fact that there are some flows that can bypass each other, and you have to reorder the packets at the destination. So of course, this is a part that you have to implement, so that the data that arrives to the GPU in the same order that it was sent. But when you apply it, you get full and optimal load balancing among all the available paths. So the second part, which is very important, is the end-to-end scheduling. So traditional architecture or techniques, they take the data, push it, every switch pushes the data to the next switch. And this creates a lot of congestion, especially when the utilization of the network is high. If you go to, if the network utilization is relatively small, then all this imperfection can actually, is maybe acceptable. But when the utilization is high, every such imperfection is causing great degradation in the performance. So what can happen in traditional architecture? There is a incast problem or load balancing problem or slow receiver problem, any problem that can cause congestion, cause the queuing at the congestion point to grow, eventually can result in PFC. And if it sustained for a certain period of time, it can result in PFC propagation. So the PFC starts at one layer and then can propagate to all the layers. And this is really blocking and reduce the flow completion time significantly. So the alternative is, instead of pushing the data into the network and dealing with the congestion that it creates, you can avoid the congestion in the first place. And the way to do it is the receiver proactively schedule the traffic from all the sources, and whatever goes into the network is already accounted for. So the network is congestion-free. And this, of course, optimizes the flow completion time because fabric switches or spine switches remain almost empty all the time. And optimize, again, the tail latency and the flow completion time. So this is the two techniques. I mean, there's a lot more to the architecture, but these are the two main techniques that obviously help in the machine learning workloads. And to actually check those workloads, we built a few, we tested a few setups. One is a lab setup that we built in our labs. This is relatively small setup. It includes 64 servers, 100 gig connectivity, and you use 4 top-of-rack switches. The top-of-racks are using, all the switches use UFI space white boxes. And the top-of-rack switch is the Jericho NCP switch. And the spine switches are Ramon cell switches, which is called NCF. Okay, and they are connected. This is relatively a small setup. And already in this small setup, you can see that the results for the scheduled and load balancing architecture that we suggested provide significant improvement for traditional systems. Oops, how do you go back? So what you can see in the result, the observation is that we run different all-to-all benchmark. We used OSU all-to-all benchmark. We did try also MPI all-to-all, and this results in same result, more or less. And we tried different message sizes, the collective sizes. This is the size of the message sent between in the all-to-all. Every server sends the message to all of the other servers. So you have a full mesh transmission. And this is the message sizes. You can see that as the message size grows, potentially there is more time that there is potential congestion in the network. And every load balancing imperfection is more visible. So you can see that you can get something like 35% better flow completion time with this architecture. Second observation is what happens in resiliency cases or when you have oversubscription between the top of rack and the spine. So what we try to do, we run the same test. And if I go back to the drawing, so you see there is many links. Like if we have 1.6T for each top of rack, so there's 1.6T towards the spine switches. And we try different, in this test, we try to reduce the 1.6T between the top of rack and the spine to less and less links and see how the flow completion time behaves. And what we can see is with this architecture, the behavior is linear. You see that you reduce the bandwidth between the top of rack and the spine, and the flow completion time reacts linearly to that. Okay? And this is, from our experience, this is not the case when you do that with the traditional architecture. So we have some result. We didn't have time to share all of it, but there's a lot more interesting result to show with different tests. This is just a sample. Okay, so this is kind of show you that even in failure cases, the system behaves linearly to the available bandwidth. And when flows, there is multiple flows. Some flow that impacted or impaired, they do not impact other flows. So this is the two test cases we show in the lab from lab testing. We also are investing in on a test setup, working with Scala computing and building a simulation, network simulation. And we have models for DNX architecture with the scheduling and load balancing, modeling the cell switch and the Jericho switch, as well as there are models for packet switches, model for the Rocky NICs, etc. And we are able to run in this model different workloads, and we can mimic all-to-all communication offload. And the important part of this is that it allows us to do the scaling easier. You can build, instead of 64, you don't need all the hardware to build this in the lab. You can build much bigger setup of multiple thousands of devices. And you can also tweak the different impairment and see how it works. So there's a lot of things that you can do, and I only show here one example of simulation results. This is also in progress. Hopefully, very soon we'll be able to show a lot more insightful data. But what we did here is we built in this setup a cluster of 256 GPUs. We built 16 GPUs per top of rack. So this is 16 top of rack switches and 8 spine switches. So in the case of the DNX...
Just a quick time check. There's 10 minutes left on your presentation.
Okay, so I'm finishing. So there is 8 spine switches which simulate the Ramon, and the top of rack simulate the Jericho switches. We partition the work. Instead of doing one collective of 256 GPUs, we partition the work to 4 collectives of 64 each, but the assignment was random. So the collective can be existing in any top of rack. So there is a mix of the collectives. And we want to see if there is any impact between one to another and how the flow completion time looks like. And we run a collective, these 4 collective, and you can see from the result, the numbers here are how far you are from the optimal, from the ideal. a score of 1 is the ideal. If you are, and you see that we are almost in the ideal result. And ideal means that how much time it takes to send a message of that size from a source to a destination based on the 400 gig interface of the GPU. So you can see here that the results are ideal. You see that the distribution is ideal as well. There's almost no, there's almost no deviation. And from some results we already have, it's very different with the traditional architecture. OK, that's it. We'll move to Mehak.
I'll just try to quickly wrap up the software updates here. So I wanted to just stress through or lean on the DSAG chassis. That's a project that most of the community here is very familiar with. Is it better? Nope. OK.
You want mine?
Yeah, so I wanted to lean a little bit on the DSAG chassis project that most of the folks here in the community are very familiar with. We've been speaking about this for the past 2 years, and the code for this is already there in the Sonic community. And the reason for me to lean a little bit heavier on this is to stress a little bit that the software for DDC is not far behind. It's almost there. In fact, it's there. And the difference between the DSAG chassis and the distributed DSAG chassis is really that the hardware components would be moved out from a traditional chassis or a box and would be made into pizza boxes. So the software really doesn't really need to change much. What we really need to address in all of this is dynamic updates and dynamic addition of nodes and those kind of things. So this is really the reason for putting up this slide, to set up a context and to let everybody know that DDC software is not one for the future. It's here, and it can be tried out today if you so choose to do so. So just a summary, and I'm not going to harp too much on this, but the key advantages of DDC. If I had more time, I would delve into this a lot more. But feel free to go and look at the Credo, Broadcom, UFI Space booth in the expo hall. It has our Jericho 2C Plus with the Jericho 2 boxes wired up in a DDC topology. And it also delineates a lot of these advantages very clearly. So I'm not going to harp on this, but please do check that out. It has a very nice presentation that speaks to these advantages. There are really 2 ways that we are seeing the DDC getting deployed. One is with a centralized sink, and the other is with a distributed sink. The centralized sink is the demo that I will be showing today. It's really, we've pulled out the components of a distributed, disaggregated chassis into separate pizza boxes, into separate hardware components, and we have truly disaggregated this particular software. The key point here being that the NCP DB sync that you see here, this has been pulled out from the box. It's a Redis database that is used for synchronizing the state, especially the NCAP IDs and the or the ARP information and the system port information that needs to be distributed amongst all the nodes for a DDC topology to work and to be efficient, as was described in Golan's presentation earlier. And this is, we end up doing all the provisioning via DHCP in our demo. And we can end up syncing the states out of band through this Redis sync. The second one that we are describing here is the distributed state sync. Now, this one has a chicken and egg problem. In a centralized sync, what we see is that when you set up your DDC, you set up the routes in such a way that every node in the system knows how to reach the centralized sync mechanism. And you don't really need to make an effort to do anything extra for distributing the state. In this case, you need the control plane up to distribute the state, but you need to distribute the state to get the control plane up. So the way that we've resolved this deadlock situation is to have a configuration file that is brought at bring up. This shouldn't be any different. This just gives you all the IP addresses of the CPUs for each of the nodes and gives you the switch IDs associated with it. And the rest is you use deterministic algorithms to decide or to reach the NCAP or the hardware indices. And so each node would individually be able to reach a consensus or a conclusion as to, and deterministically reach that conclusion as to what is the VMAC and what is the NCAP ID that is being programmed across every box in the DDC. So it eliminates the need to distribute a state to bring up the control plane. Once the control plane is up, you can use that control plane for distributing the rest of the state as is needed. So this is one aspect that we are still collaborating, and we continue to collaborate with a lot of our partners to get the distributed state sync up with the DDC and to make that available to the community. I'm going to skip this in interest of time, and I just go directly to the demo for this, and this will probably show you most of the things that we are speaking to. How do I get the demo into this? OK, here. Wow, there is a.
We have about a minute.
Oh, so I'm trying to, OK. I'm trying to see how to get the. How would I be able to get the demo up? No, there's no audio. I was going to speak to it. Yeah, but I'm not able to see most of it on my screen.
Scroll down. Yeah, you see the play button right there? No, you move your mouse to the right.
Oh, OK.
Yeah, right. Yeah,
OK, I'll have to see this screen. Oh, OK. Perfect. Thank you. So this is the DDC topology that we used for doing the setup internally. And what we ended up doing was we set up a ZTP server. Using the ZTP server, we set up most of the configuration. The first thing that you see is that, as I mentioned, that we end up setting the chassis DB address. This is deterministically set up right at the beginning. So this demo is about a centralized sync. So every node in the system, aka each of these nodes, knows how to reach this centralized server. And the centralized server is what is used for distributing the state that is needed to be synchronized across all nodes for sending your information and to give the operation of a chassis. This is just going through the provisioning server. And with ZTP, we end up setting most of this configuration up. Then we are bringing up the boxes here using ONI. And what this demo is showing you is we first bring up the one NCP and the two NCFs. The NCFs are nothing but the fabric nodes here. And the NCP is the Jericho 2C+, which is the leaf device. And we are bringing this up, and we are not yet adding the NCP2 into the DDC topology. We will then add the NCP2 into the DDC topology, and you will see that it will get discovered on the NCP1. So as we do a show BGP, just a second here. So here you can see that these two BGP addresses were never discovered. So this is the backplane IBGP. But you see that given we've only brought up NCP1, you do not, and you cannot discover the BGP IP addresses of the second box or the second NCP. One thing that I forgot to mention is that this is a UFI space box. Each of these boxes has got two instances of a Jericho 2C+. Based on the DSAG chassis architecture, we are running two sonic stacks on each of these boxes. So NCP1 runs two sonic stacks, and NCP2 also runs two sonic stacks. Effectively, you have 4 BGP routers in this network discovering each other to start forwarding traffic. So the second box has started to come up. We installed the firmware image. We started the ZTP process. Using the ZTP, we are overloading the ZTP server here as a controller as well. So all the day 0 configuration gets pushed down at one shot to provision all the IP addresses that you need on the interfaces at get-go. Now we will see that as this NCP2 has come up, as you see here, 333.5 and 333.7 do get discovered. This is the NCP2 discovering NCP1. And we'll also go back and show to you how the NCP1 which was showing earlier as having not detected the IP addresses of the NCP2, will also have discovered it, and the full IBGP meshes up. And as a final step, we'll just do a ping for all the 4 IP addresses from all the 4 BGP stacks or all the 4 sonic stacks to show that every node or every sonic stack has detected each other and your DDC is ready for forwarding. This is back to NCP2, where we'll also do a ping from the NCP2 to show that the NCP2 can also ping every node on the NCP1. So yeah, that's all that I had from the demo. As a final, and I'm not going to try to waste everybody's time to bring up the call to action slide, but as a call to action, Broadcom is going to be contributing the code or the fixes that are needed to get the DDC working. These fixes are a Delta fixes, and I stress again on top of the DSAG chassis. I believe there's a DSAG chassis project also. If you need to, presentation today, if you need to learn more about it, please attend that. And these fixes will be working on top of the DSAG chassis project itself. And we will also be trying, leaning on the community and looking to the community to help us solve some of the more complex problems, like how to have an active-active or a more resilient supervisor server solution, how to add dynamic nodes into the network without a priori provisioning all system ports in the network. And we will be having a lot of discussions in the community moving forward on the DDC use case. Thank you.